Alright, listen up. I've been thinking about this on and off for maybe a year. You've seen the title, you know what we're here for, let's go. So, first of all, spinning, rotating, you're all familiar. There are two ways to explain my question. The first conversational, and the second mathematical. We'll start with the conversational one. This is a circle. It's rotating, can't you tell? No, you can't, but now you can. How can you tell? Well, because those spots are moving around in a circle. In fact, let's look at just one dot, and let's hide the circle. So, when an object is spinning, the various points on its surface move like this. Wonderful. In fact, it doesn't even need to be a circle at all. This is just what happens when things rotate. You can select any one point, trace its movement, and see that it's going around in a circle. But hold on. Look at that. Isn't that funny? The closer we get to the center, the smaller the paths they trace. Huh. Well, not exactly. That's just because the point we're rotating around happens to be the center of the circle. You can see that if we select a different point on the circle to rotate around, now a point's proximity to that point is what makes its path smaller. But here's the thing. That point the circle is being rotated around. Why don't we try follow its path on each of these circles? Okay, maybe let's just pick one and zoom in. It's a pretty small movement. Zoom in a bit more? Yeah, the joke is that it isn't moving, okay? The joke is that there is no path to follow. I hope you're able to keep up with the quick wit employed on the Chimney channel, because people do get left behind here. But that's not fair. Remember earlier? The only reason we can't tell it's spinning is because it's all one color. Sure, that point we're spinning around isn't moving, but it would still have to be rotating, right? Just rotating in place, the same way the circle as a whole is. If we just add a couple of spots to it, we can see that, nope, stop right there. That's the kind of talk that gets you left behind. Sure, that logic tracks if we're talking about the area kind of around the point of rotation, but if we're talking about a single point, there is no adding smaller dots to it. That doesn't work. It's a single point. You can't isolate an individual part of it to compare. It has no parts, it's one point. On something like this, where the point of rotation is not a part of the shape, we can say that every single point on this object is rotating. The same here, and here. But in something like this, where the rotation point is a part of the shape, I think it might not be enough to suggest that it just isn't moving. I think it isn't rotating at all. Here comes the more mathematical explanation now, and it's actually pretty simple. As we select points closer to the point of rotation, the amount of movement they do with each full spin gets smaller and smaller. Look right here, it's a tiny path. On a circle with a diameter of 10 units being spun around its center, a point that is 5 units away from the center will move around the outside of the circle, tracing a path that is 10 pi in length. A point that is 2 units away will follow a path that's only 4 pi in length, because we're basically drawing a smaller circle inside the circle, and a circle's circumference is twice its radius multiplied by pi. If we move only 1/4 units away from the rotation point, now we're tracing a circle that is only half pi in length. Basically, the distance any point will have to travel with one full rotation can be easily graphed with the equation y equals 2 pi times x, where x is the distance from the point of rotation, and y is the distance of the path traveled. Very easy equation. Explaining it in detail makes it sound complicated because it's a lot of words, but it's just a straight line. And look, when x is 0, or in other words, when the distance from the point of rotation is 0, i.e. when you are at the point of rotation, the distance of the path traveled is also equal to 0. This isn't even a case where the equation tends towards 0 and we're getting all mathy and theoretical. It's just, boom, intercepts the origin. The answer is straight up 0. And there should be nothing to suggest that such a point can't or doesn't exist. Negative values for x, sure, they don't exist in the real world. You can't be a negative distance from something. But there must be some point we are rotating around, and that point must be 0 distance from itself. Cool, okay, we proved that the point of rotation follows a path of 0 length. That's wonderful. So now we know that it stays in the same place. But how do we know that it isn't spinning in that same place? Well, we kind of don't. I think what I'm basically getting at here is that I believe there is no such thing as rotating a single stationary point. I don't think it is possible. Let's look at our original circle again. It's rotating right now, but you can't tell, because rotation is entirely relative. A single point cannot rotate because there is no way to compare one part of that point with another. It is a single point. In the same way that this circle, as it rotates, is constantly replacing each of its purple pixels with an identical purple pixel, such that you can't tell it's rotating, a rotating stationary point is constantly replacing itself. It is not rotating because nothing is happening to it. So sure, an atom will rotate, an electron will rotate, because neither of them are points. But in theory, if you go far in enough to see the individual point of rotation, it will be entirely motionless, and it will not be itself rotating. So when you spin a circle, for example, all of those other points are moving, rotating around, tracing a circular path. But the point in the middle, the point which is being rotated around, might just stay entirely still. Isn't that interesting? Thanks for watching this video. It's just a little thing I've been thinking about for ages, and I wanted to get it out there. You might think it has no real-world applications, but I would counter that by saying it is interesting. And that's an application enough. Okay, bye. I got a lot to do.